Hello everyone. Today we are going to learn about the Truss structural analysis programming, which is to be done in Octave, which is equivalent to MATLAB, but Octave is the free version. So we will start with the problem description, which is a truss structure. I will explain this in the writing on the iPad first, and then the next half of this video will be done on the Octave program. So first of all, let's take a look at the problem that we are going to analyze.
Structure is dimension in the following. I feel much better these days because I think I am older than maybe all of you. When I start my career 10 years back, I was 27. Students are older than me. And I feel like it was quite funny. And I don't get the reason why I try to struggle to graduate my PhD at that very early age. Too young. I don't feel that it is good. At the age that I should enjoy life more, I start my career. Start teaching. That is okay. Simple truss problem. The height, not 3, this is 4L. We just need to come up with some problem in order to just understand the architecture of the calculation. So 3L, all 3L, and then I will name all the points. Basically we will need something like the coordinate. So we have the x and y coordinate. All the nodal points right now we can define them, and actually this is the way the computer structural analysis programs do, right? They recognize the nodal point, they don't recognize the member. So let's look at the point. That depends on how you name the node. So I will name the node in the way that makes your matrix looks just crazy. Well, generally we name the node like the node number 1 and node number 2, they are connected by one member. Okay, so when you construct the stiffness matrix, it is quite dense. But if the node number 1 is on one side and node number 2 is on another side different, and the node number 1 and the last node is connected by one member, that's gonna make your matrix so sparse, so you're gonna see everything flies around all over. The non-zero value are not compressed in the diagonal band. Okay, it just goes off diagonal very much, and that is called sparse matrix. And you generally can see the sparse matrix in a finite element in direct stiffness approach. That depends on how you set up the node numbering. In the past, when the computer program is not capable of solving the sparse matrix, this day we call it sparse solver. It doesn't collect the zero value. Okay, so in the past, people try to put things in the diagonals, try to make things close in the diagonal. I should maybe show it like this. So basically, this is the diagonal band, non-zero, and then you have a zero in the off diagonal. But if your first node here and the node number maybe 10 is here, okay, then you will have something here and you will have non-zero values out there, right? You will have more and more off diagonal values. Okay. So the primitive structural analysis program tries to compress this diagonal band, and they use some thing which is so-called skyline solver. This is just the history. You don't have to use this thing this day anymore. So the skyline solver, well, this will look like a skyline. Yeah, this thing looks like a skyline. It looks like the building. Okay, and when you look in one column, you find where is the outmost non-zero value, and then you define the skyline from that point. Maybe over here you have non-zero value here, and then you have 0, 0, and then something. Okay, and above is 0, 0. So this defines your skyline, the highest point where you have the non-zero value. So there's this affect the data storage techniques, and people try to make the solver to improve the cost effectiveness of the solver, because if you store too many zero, well, zero is zero. They don't need to store a zero, right? So they try to minimize the storage of the matrix and to make possible for the larger and larger problem. But that's a primitive technique. So skyline solver seems to be a very advanced one in the past, but this day we use like a super solver or super LU solver, which deals with the sparse matrix, and that get rid of all zero entries from your calculations. So you keep only just the non-zero values. I am not so sure if I used to talk about this, but if you consider this, you will find that the level of storage are totally different. For example, if you work on the Truss problem, or a Truss problem or bar problem, the stiffness matrix is after the transformation into global coordinates, you're going to have the 4x4 matrix, right? So the 4x4 matrix, if you condense it well, if you name the node very well, for example, if you have the very simple problem like this, 1, 2, 3, 4, 5, like the exam problem, and then DOF 1, 2 will be connected with DOF 3, 4, like that, 3, 4 connected to 5, 6, and so on and so forth. So this is how your assembly of stiffness matrix go. So you have this band, all right? We call it bandwidth. The width of the band, okay, the bandwidth is 4 for this problem. Okay, so if I have maybe this goes like to the 1000, the node number goes to the 1000, so 1000, that makes 2000 in this dimension, right? 2000 row, 2000 columns. So 2000 row and 2000 column, that makes the storage of this matrix being 4 million, right? You need 4 million slots to accommodate this matrix 2000 by 2000. But in fact, the non-zero value is actually just 2000 rows multiplied by the bandwidth, which is 4 to 6. Actually this one is 6, because the one that is overlapping and non-overlapping, so you have the 6, right? The widest location is 6. So if you take the 2000 multiplied by 6, you get much less, 12,000 in comparison with 4 million. Okay. The bigger, the worse. So if you go with, like, instead of 2000, you go with 100,000, it's square up, right? So the n row, if n is a number of row, so you have 6n in comparison with n square. So if n is small, like 10, you don't feel the saving of just using of just collecting the diagonal band. Whereas when the n gets larger and larger and larger, the n is square. So when it is square, then the usage, the storage required is going up very quickly. So this is the problem for the solver in finite element analysis. If you store everything in the matrix, in your stiffness matrix, that is very bad. You're running out of storage, and the storage what we talk about here is the RAM, not the hard drive, because you need to put the temporary data into the RAM, and then, well, it's gonna compute and do all the things. Hard drive is a permanent one, and you just put it there for long term, but during the calculation everything will be on the RAM. So that depends on the RAM of your computer. The bigger the RAM is, it accommodates larger problem. But, well, you can see that it is stupid to accommodate the large problem by just buying more RAMs, right? Because the requirement is n square. That's huge, and you can go the other way around by using the sparse solver, S-P-A-R-S-E, sparse solver. So the sparse solver, essentially it does this. It eliminates the non-zero things. It doesn't collect it doesn't collect the zero value. It keeps only non-zero value. And even though your non-zero value is out there, it might be scattered a little bit because of the nature of finite element calculation, but still it still can manage to work. So the non-zero will be collected, zero will be all discarded, and you save a lot. And then you can analyze much larger problem with the less cost than collecting the whole thing. The solver, I just talk about the solver to this much. I talk about the super LU or the MUMS solver. You can look up in the internet and Google for sparse solver. The code is available for Fortran code, for C++ code, sometimes even for Python code, or even in MATLAB we can use it. So you need to do some sort of compiling. That's going to take a lot of time for you because you are not familiar with Linux or Unix operation system. You need to compile, you need to make the file in order to use it. But once you get it to work, that is a very powerful tool for the serious computations. If you do finite element, you're gonna really have to look at the solver if you develop the code by yourself. But if you just a user level, then the embedded solver in the program like Abacus, ANSYS, or even in the SAP, okay, structural analysis program like this, they use a sparse solver already. Just know that. And then you have to define the node number. So the node number, we give it 1. I will set up the node numbering in the bad way, and your matrix will be very sparse, and you will not enjoy it because hand calculation or hand plugging in is going to take your time until you get the first son or daughter. Alright, it's gonna be so long to plug in all the entries from element stiffness matrix to the system matrix. So you will be that old, get married, have some son or daughter, and then you finish this up. Problem is very long. But if you just go ahead with the coding, life will be beautiful. So 3, number 4, number 5, number 6, and number 7. We will identify the coordinate of each point. But for now, I think this is good to do. So note the degree of freedom numbering will just go in the way I talk. 1, 2. Okay, we start with the x, right? So the x start with the first and y come later. This is 9, this is 10, 7 and 8. You can just watch. Actually, but depends. Sometimes you feel like you can learn things better if you write things down. So that's up to you. Okay, I'll share this material to you, of course. 11, 12. Okay. Degree of freedom are all defined. Then we need to define the element. So element will be defined just now. Let's make element number 1 here, element number 2 there, element number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10, 11, things flies around. Okay. So members defined in blue in the rectangular shape. Node number in red in the circle. Degree of freedom in purple color. I'll give you the EA information a little bit. EA. What? 3 EA. 3 EA. EA. Oh, defined. Very well defined. So in total you have 7 points. And you have how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. What else? I give you the coordinates. So the first one is 0, 0. The number 6 coordinate is 6L, 0. This one is 12L, 0. This one is 18L, 0. Number 5 is 3 and 4. What else? 1, 2, 3. So this is 9 and 4. And 15L and 4L. When we conduct structural analysis, you don't want to calculate the length of each member by hand. You don't want to find the orientation of the member, the alpha angle by hand, right? That's something the computer will do. So when you use SAP, if you used to do or maybe you use Stat Pro robot, wherever Revit, when you construct the structures numerical model, you click. Well, very first thing you define the grid line, and then you click and drag and drop. Okay. So the first click is the definition of the coordinate of the first point, starting point, and the drop is the coordinate of the ending point. That is just done by clicking. Okay, but if we look in the programming point of view, you define 2 nodal points coordinates, but you never really do hit the calculator and find the length and find the orientations, because you already defined the 3-dimensional space or maybe 2D space in the program. So that is your playground and your structure will be in there. So the information stored in the program, the data structure, should be gonna talk about the data structure a bit. First, nodal point coordinates, right? This is important because from nodal point coordinate, if you find the distance between two points, you get the length of the member. And then if you get the length, you'll be able to define the angle next. The orientation could be calculated from that too. You get delta x, you get delta y, you find the angle orientation by the arctangent value. Okay, that's it. So the nodal point coordinate depends. 2D problem you have x, y, 3D you get x, y, and z. So the program we're gonna make will be the 2D. Actually, you can extend to 3D very easily because it doesn't really take much more to do the 3D. But the graphical presentation in 3D is just difficult. I draw the truss in 2D plane. It is much easier to understand when you do it 3D. It could be hectic. So we will call this the x, y, this will be the name of the variable I use in the program. Okay, so explanation is here. X, y, is a nodal point coordinate. How does the data structure look like? So x, y will be the two-dimensional array. So you have x1, y1, x2, y2, xn, yn. This programming is not limited to just this problem. This problem is just the dummy that will show us what we need to do in order to analyze, to set up the infrastructure for this problem. But basically the framework here is applicable to all kinds of truss structure, right? So later on, you just drop in the xy coordinates. You just say that, okay, this node and this node connects by this member and gives the information about loads, then boundary conditions, and structural analysis will be performed by this subroutine. Right? So this is generalized for all the problems. So this is n by 2 columns. First column associated x, second column is associated with y, and you have in total n rows. So the first row node number 1, node number 2, node number n, so this 2D matrix, two-dimensional array, store the geometry of the node, locations of the node. Next step, you don't use just the node, right? You will use the node to define 2 points of your member. That means some array that tells the connectivity has to be there to define the member. I call it nodal point mapping. Nmap. The nodal point mapping is is done by the element. So one element connects 2 points. So this maps for one element to the node. So if you have number of elements, I call it NELE. And number of nodal points NDE. So you can guess for the N map, how many rows do we have? We have number of rows equals to NELE. Alright, we have the element number 1, and then inside you have nodal point number for starting and nodal point number for the ending, NS2 and E2. So, for example, if we look at the element number 1, you can define the starting node or ending node. Well, you can define the number 5 as a start or ending. It doesn't really matter. If you have the span loading, then you just need to apply that correctly. Just that. But no matter how you switch, the program will take care of the orientation automatically, right? And then you will end up with exactly the same thing. If the starting node is number 5, the angle will be counted from X, go all the way to here, or minus of this angle. For the number 6, it will be from here to here, right? Or minus from here to there. It doesn't make sense to measure it this way, right? So the program will be written to measure the orientation in that way. Okay, I think I point on the board and you will not see that on the screen. So if we use the number 5 as a starting, so it goes like this, or the negative of this. Whereas if you use the number 6, it goes like this, or the negative of this. Right. Well, that depends on the calculation we're going to make in the next step, right? But it will be generalized for all cases. So I give you this node number 1, 5, 6 or 6, 5, whichever. Then how about number 2? Element number 2, where is it? Here. You can do the 2, 4 or 4, 2. So that depends. It's up to you. To the last element number, I think 11. 7337, whatever. So we are doing this calculation in the semi-manual approach. The semi-manual approach, then you can understand it from the point of view where you are the human being, and another point of view where you are a computer trying to understand the source code. Okay, this explanation right now is not exactly the approach we do previously, because previously you don't want to find out coordinates, you don't want to do anything like this. You just do things by just looking at the length of all members. You get the EL of all member, you try to measure the angle, the orientation, and then you do things in the way that the human brains understand. So this is actually more logical. If you can explain to the computer and computer work for you correctly, you are a logical person, and that is the truth. I think we are generally we as an engineer, we are actually more logical than other people already. But we will be more logical if we can talk to the computer. Okay, so to the extreme, and you will end up getting married with the people in the same field, because you cannot talk to the people in the other field. People will not understand us. Okay, you are too logical at one end. At the end of your thesis graduation, you'll be a different person, which is good. Next, let's see. Okay, node number 1, I will drop in the number 0. How about the number 2? 15 and 4. How about node number, the last one, 7, 12L0. So this node 1 and node number 7, element 1, element 2, and then element number 11. This process here, manual. It is the input. Well, you can say that, well, I use SAP, it is not manual. You don't need to fill in the number 6524 manually. Well, that is possible via the graphic user interface. GUI. So the process over here is the process where you input the computer will not know what structure you want to analyze, right? If the computer knows that level, that means it has to be the artificial intelligence level to do this for you. So right now you still get a job because you will do this. You will click and construct the model in SAP, in ETABS. But once the AI is fully developed from the architectural drawing, the AI will convert the architectural drawing to the structural model, numerical model. This is the process. And it doesn't look like it is difficult at all, right? To click and then construct the members. This is the shell, this is the slab, this is the beam, this is the column. And the procedure is just identifying the coordinates. Fine, the AI will do that. Identify the members. Well, it still needs some judgment from the engineers, but that development is not too far to see in your lifetime, in these 10 years. So this green thing, right, still manual, but it will be taken very soon by the AI, of course. But now you just know that, okay, here is your role to do it. What else? You have the node number, you have the element number. From this point, well, I don't mean to discourage you or make you feel depressed, but that's the reality. It will be soon, so you got to think about, okay, what to maintain your role, the importance of your job. Sorry. So from this point, the next step, what will be computed? Length and orientations. This is programmed to do, right? You will let the algorithm work for this. The length, high school student can do it, right? So you get the delta x1 minus delta x2, square it up, plus delta y1 minus delta y2, square it up. Just that one line, you get the length already. It doesn't take time. The orientation, still easy, right? Arctangent. So orientation, if you want to find the angle, alpha, right? We use the alpha. Alpha is equals to a tan, which is the arctangent of. I'm sorry, it shouldn't be delta. No. Let me just this. It will be just x minus x, y minus y. It is not delta. Sorry. So x minus x, you get delta x, y minus y, you get delta y. Arctangent, of delta y, right, divided by delta x. Well, you need to concern about the delta y and delta x that this ratio could be the same for two quadrants, like the quadrant number 1 and quadrant number 3. It could be the same ratio, or quadrant 2 and 4 could be the same ratio. So we will check the value of the delta x and delta y. So the sign will tell us that which quadrant that this point stays in. Okay, so we can I will put the conditions into the code later, and we will determine the quadrant number and be able to identify the angle precisely. The thing is that the program like MATLAB, when it computes the arctangent value, it will report just maybe like from minus pi to pi, right? That's the range that the program will report. So you might need to just work on the determination of how the angle looks like actually, because this is for example, this point, you end up with the same angle, same tangent value. Delta y here, which is positive, over delta x here, positive over positive, you get positive. This one negative, this one negative delta x, so you end up with positive. So tangent value is same, but MATLAB or Octave will report this angle. It will not report this angle, because the angle will be reported from like minus pi to pi to in this range. Okay, so it is our job to determine precisely which one, because sometimes you need this angle. This one is not wanted. It changes your information. That's the thing. So that will be inside the programming, but for now I just show this, that here is what is determined by your computer. So you know the node number. When you construct the element stiffness matrix, it is associated with the local degree of freedoms. So your node number will just bring the 4x4 matrix, every entries in the 4x4 matrix, to the system of equations. So the mapping, this tells you the route to the final, to the destination in the system matrix, right? So for the 4x4, it is DOF1, DOF2, DOF3, DOF4 local. How to plug into the right place? You can do that already, because you have done homeworks, you have done exam, you know how to plug in. But that is the procedures that is going on in your brain, and you really never define it into the line by line procedures that you can, well, that is more logical than actually the brains understand it deeply, but to write it out precisely what is the logic of doing that, here we are going to use the node number we have in Nmap and then link it to the destination location. Okay, so we start in the Octave. For now, let me just put the directory. Why is it just C? Maybe D. Okay, storage. Put it in the class video here. Can I create the new directory? Octave code. Okay, that's just Octave, right? Okay, so this is my working directory. I am inside this Octave directory. I'm gonna put the file, the M file in there. So here, let me save first. Good. Main. Just that. So function main. And what do we need? Clear all, close all, CLC. We will put the sharp sign over here to comment things. And first of all, we will talk about the input. Believe me, you don't need your laptop. As it is recorded over here, you type down, you try to catch up with me. You look at the screen, you try to type it down. You might not understand. The best way, just sit back, relax. It's like you are taking a flight. The video will be there, okay? The file will be there. I will give you both the file and video. So you don't need to follow this process. It is the best to just relax. Try to relax in this class. Okay, so here it's gonna be the input. Actually, you don't need to make it look beautiful, but I am the person who do not like the code that, well, you come back. There are many kinds of person. I'm the kind of person who make the code, try to make it very organized, but I really never come back. I rewrite the code. I don't understand myself because many times, I have like probably 10 codes doing structural analysis in the different architectures, and every time I come back, I just rewrite a new one. I want to do the plate bending, I rewrite a new one because I don't want to try to understand the old code. But maybe you don't want to do it that way. I am a strange person. Okay, I got to accept that. So I just redo it again and again and again every time. I have the reinforced concrete cross-section capacity calculator by the fiber model, and I have many files I done, and every time I want to do it again, I just rewrite the Excel spreadsheet. It is just a strange habit, okay? But for the people who are practical, okay, it is more practical to come back to your old code. You should keep it well, and then you explain everything in the code well, so you come back and you'll be able to modify. It is better to start from the building, not laying the first brick again, right? Waste your time. I just consider that like the exercise for the brain, so I just redo everything. Input. So what you need to input? The structure will, the program will not know anything about your structure. So the geometry of the structure, description of the structure has to be there. NDE, the number of nodes has to be given, and the number of nodes we have in this problem is 7. NELE, the number of elements we have in this is 11. Okay, actually for this input phase, you can write the program, the piece of code that, well, your MATLAB can read from the Excel format file, can read from the .txt file, the text file, like, well, you can use WordPad, you can use Notepad to generate that sort of file, right? MATLAB will read that. Or the Excel file like .xlsx, .xls, or even .csv, okay, comma separate something. You can Google up for CSV, what it stands for. But it has the interface with the files from outside, and it is actually better. I show here because I'm not expecting this code to be the code for everything in this world. I don't need to facilitate that interface. All right, it wastes my time. We need to learn about the coding for structural analysis, but in the practice, the input will be one separate file. Right now, I make the input inside the M file, which is well, you're gonna need to come into this M file and modify it every time you change the structure. So this is sort of not practical or not appropriate for the programmer, because you don't want to touch the software once it is verified. You don't know if someone who doesn't know or doesn't understand things in this main.m and by chance delete the minus sign, delete something, and then ruin the whole code because one has to come in and modify the structural information. Okay, that is not good. And moreover, if you have the input file like the text file or Excel file, you're gonna save it to the version. You can modify it many times, and then you can keep the records of your input file. In for example, you have the first version of your structure, the second version you just adjust the name, change the name, description of your input file, right? And then whenever you want to run, you just call the right input file, and then you get the result you want. That is the same thing as in other structural analysis program like Abacus or ANSYS. Most of them you work first, like even in SAP, you work first in the screen. You have the graphic user interface. You see the line, you click, you drag, you drop. Okay, that procedure is how you construct the model. But once you finish your model, the program, structural analysis program and FEM, will construct .in. .in stand for the input. The .in, well, you don't recognize this file extension, but if you double click and try to open it using the notepad, WordPad, it will show you the text file, and then it tells you number of element and the matrix of your nmap, the matrix of your xy coordinate. Everything comes up in that input file, and it keeps just the text file. It doesn't keep that graphic, okay? Because the graphic user interface will come into this input file, extract the information, and then render the lines from this input file. It is the best storage of structural geometry and description. But over here, I'll put it here, okay? This is just for education purpose. If you do research, maybe you consider it in the other way. You write the input file for some spatial analysis you need to do, spatial calculation you need to do, and then store and save many input files. For here, if you change, once you change, then the old information will be gone. And the old information, as it is gone, you cannot track it. Why? Because you run the program, you get the output, you might not save these things in the input along with your output. So once you come back again, you see the output file, but you have no idea about what is the structural description. That output is totally useless. You have no idea about boundary condition you put before. Well, maybe like many days ago, and then you come back and see, okay, you have 5 output files, but you have no idea. The first one is generated from what basis, the second one is from what basis. So it's totally useless. But if you have input file, you have the track record of what you used to input, and then you will match it with the output. It could be the plot, it could be whatever format, fine, but you can match them, right? Knowing output without knowing input is totally useless and waste of your time. Okay. What is the next thing? XY code. XY code for here, as we're gonna input that in. Okay, I just put it over here. Should just do it this way. So XY code, let me take a look. First of all, the coordinate, first one 0.0, and then you need semicolon to come down to the second line. What 15L, so that means you know that L will be somewhere right in your calculation. Once you get the results, which will be just the figure only, you need to know that what will be the scaling of those figures, because the L will be pushed in group with the EI L square, right? That will be a group of variables and you need to scale it back. But over here we will just put 15 and 4.0. The reason I put the 4.0 15.0 because I do not want the program to understand that 15 is the integer, right? The program treats the values differently. The integers one way, the float or double precisions in the different way. Integer, well, 1, 2, 3, node number, element number, number of boundary conditions, that should be integers. You cannot have 4.5 boundary conditions. You can have 3.1 elements, all right? That should be perfectly integer. How about the float, the double precision or single precision number? These are the number with the decimal point, decimal places. So double precision will be the highest the highest precision one in the system. So we generally use the double for the numerical simulations. Okay, so we go with the double precision. That will be for what? For the structural properties. Maybe the length is 4L. Maybe it is 3EA. But that 3EA, that 4L, they are not the integer. 3EA means 3.0000 EA, right? You can have 3.5 EA if you want. You can have 7.3 L if you want. So these are the different type of information. It is the float or the double precision. You have decimal places on the back, and that's to keep at least 0.0 there. Just remind us that this is the float, this is the double precision. And in many program like Fortran, the lower level kind of program, it's gonna need you to do this. You cannot just put MATLAB is very user friendly, but due to that user friendliness, it is not strict with you. Well, you think about the compiler. The compiler could be Fortran, could be C, could be MATLAB, could be Python. The compiler is like your instructor. The strict instructor will be making your habit better than the less strict instructor. You feel good to stay in a class, but you might not be as much behave as you are in the strict advisor or instructor class. Why? MATLAB will not report any error. It will not blame you. Okay? You say 7 or 7.0, it doesn't blame you. It tries to understand you. But you know, trying to understand is an algorithmic effort, trying to understand. In contrast, Fortran will not try to understand you. Fortran, if you want to come up with one variable, life will not be just like this. Put the name equal to 7. It's not like this. In Fortran, you need to define that the NDE is the integer. And what kind of integer? You can specify clearly how many bits of integer. Because sometimes if the number is around 1 to 100, okay, you can use less number of bits. If the number could be million, trillion integer, but trillion level, then you use more bits. So the management of the data is more strict in those programs. Well, as a result, the program compiled from Fortran, compiled from C is faster than MATLAB. Because MATLAB is very flexible, so it spares you so much space for your flexibility. But those programs very tight. So you need this much, you need to think about how much you will put into this variable. If you think that it is about this much, then okay, integer 4, integer 8 bits, integer 16 bits, you plan everything ahead of time. This one just make you less smart than that kind of program. But that kind of program is gonna make you like a computer science people, so I don't want to drag you through that far. So I don't teach Fortran in here. But actually first I intend to teach the Python in here, but well, I am not happy with something with Python a little bit, so okay, stay with Octave or MATLAB. Number 3, maybe you can help me. Okay, node number 3 is what? 18 and 0. Number 4 what? 9 and 4. Number 5, yes. 3 and 4.
Number 6 and 0.
6 and 0.
Number 7, 12 and 0.
12 and 0.
Number 8.
Yeah.
No. Only 7.
Only 7? Okay. So this is done. Then we close the bracket and then that's it. Well, to make, well, this code is for education, so we write this down. But if I just do it, I will not have to node number. Oh, sorry. N2, node number 3, node number 4, node number 5, 6, node number 7. So you come back, you can understand this easily. I just put this down here. XY core is there. The next thing is Nmap. This explains you how the member connects the node. Okay, Nmap explain how members connect to the nodes. Okay. Yeah, I think in the future then I don't need to repeat this for sure. I will put this on YouTube, and next year I will not open this extra class to drag people through this programming, because everything is given in very detailed information like this. Actually, I do not really have to come to the class in the next year if everything is recorded. And I am useless and I will die because I am useless. XY core gives the X and Y coordinates of nodal points. Okay, so Nmap nmap right now we are talking about integer, so if you put something 0.0 on the back, the program might get confused. But MATLAB is too smart, so that algorithm will try to understand 12.0 being the node number 12, but it's not good to do that. As the program has its own effort, that is dangerous because you don't know how the program may react to something stupid you put in there. All right, so try to be as smart as possible when you input things to the program. It doesn't report things, doesn't mean that everything was done successfully and correctly. All right, you don't see the error. You have two kinds of error. Syntax error, you use maybe the wrong if, the wrong for, the wrong comparison, the syntax, all about syntax, so that will be reported. Sometimes it is about your algorithm. Let's say you define the array of which the size is 100 by 2, and then in the program you keep looping on, and then the program try to access to the entry number 101, 2, which is not existing, right? Because you predefine this array to be 100 by 2, so it has just 100 row. You try to access to the row number 101, which is not existing, then the program will report such error. So it is semi-syntax error. So you are not wrong in the syntax, but your code just try to get something which is not existing. The next kind of thing, well, these first two error will be reported. So the command window is gonna show the error when it executes the code. But the third kind of error is very dangerous. It is from your algorithm. You just get the wrong thing, multiply to the wrong thing, and then you get some number, and that number will be used in the next step, and next step, and at the end you get some output. And then first time programmer always have too high level of confidence, literally too high. When I tell you go back and check your code, not you, well, your senior, which they were the first time programmer, okay, before. So they came approach at the end of the class, sir, I rewrote the code and I'm sure that everything was right, but I still get this error message. I say, well, if everything is right, then you don't get this error message. And you go back and find it out, there must be something wrong. But, well, it couldn't be like you did it right and the program just give you the error message, or the program returns you the wrong output. If you do things right, there must be something wrong, and your eyes will not be able to check it. Sometimes you need to go have a shower, try to forget about it, because if you go line by line of the thing that you do, you believe in yourself. Yeah, this line is correct. Yeah, the next line is correct. Yeah, the next line, they are all correct. How come it is wrong? No, you got to believe that you are wrong first, and then you will find out what you did wrong. If you believe that you are right, you never find it. Yeah, this looks very good. Yeah, this is absolutely right. Yeah, this is perfect. And how do you find the error? You cannot. Maybe your friends can look for it, but well, as the code gets bigger and bigger and bigger, nobody is going to help you. And programming is very good in terms of making you like a self-independent. When I did my PhD, I have a piece of my code, something goes wrong. I spent 1 year to debug it. and you just, I cannot just cry around asking someone to take a look at my code and fix the bug. Sometimes you have to even rewrite the whole piece of the code because you cannot really find the error in the old one. So to rewrite it, sometimes you have the different perspective. Hey, maybe this point here I should do it this way. something could be hidden, right? And the best practice, make it module by module, so you will find the error easier. So let's look at the end map. 6, 5. The second element 2, 4. The third element 6, 7. Number 4, 2, 3. Number 5, 4, 7, or 7, 4, up to you. Number 6, 5, 4. Number 7, 1, 5. Thank you. Number 8, 1, 6. Number 9, 6, 4. And number 10, 7, 2. And number 11, 7, 3. Thank you. Close the bracket. There. Maybe I highlight this point here. At the end, it switch around a little bit. The bracket closer is coming before the semicolon here. Alright, if you just switch this position, then the bug comes up, and you'll be frustrated. So over here, this is element number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. As of now, actually, we can do a little checking. If I were you, okay, in general, I will check if the input geometry is correct. You draw that truss in your iPad, your paper, and then you try to migrate everything into the computer. But if you never really check if that X, Y value is correct, then you are analyzing the wrong structure. Well, if you click in the SAP, then graphic user interface will prevent you from that problem. But if you use MATLAB to construct things from the scratch, from the XY coordinate, or many times you have to mesh by your program, well, in FEM, you have your own mesh generator. So at least you should check and see if you come up with the structure that is exactly the same as what you want to analyze or not. So we need to display this information. Okay, so I will plot the structure. Right? So in order to plot, well, when you plot, what do? You make a line, okay, from starting node to the ending node, right? So it should be hold on, and then if you want to plot, it is the operation of drawing line from 2 points, but that operation will repeat, right? Because you want to draw every single member. If that operation repeats, how many times that the operation repeats? Equal to number of elements, right? So we are going to learn about the for loop. So if you have the operation that repeats, this time this structure you have 11 members. The next structure you could have 100. And then you will not come back and write the code to draw the line one by one. The program can do the loop. So for is the very useful. For I equals to 1 to NELE. So what is the meaning? I will be the integer. You can use J, you can use K, you can use your name, right? For Sivaram equals to 1 to whatever. Equals to 1 means the loop will start at the counting equals to 1. Some people, the computer science people, they like to start the loop with 0. That is very confusing, but if you want, then you for I equals to 0 and 2 instead of NELE, then it has to be NELE minus 1. Alright, but yeah, I really hate that. I don't know why. Their logic might be different from our logic. One step left. You can do 1 and 2 and NELE. Then the I will be increased at the increment of 2. If you don't put that 2 in there, then the increment will be 1, automatic 1. So first time I equal to 1 and 2 and 3 until NELE, which is 11. But if you put the increment of 2 there, then it could be like 1, 3, 5, and on and on and on, right? I don't use this much, but you have the freedom to use it. And then, so from this 4, we want to plot. In order to plot, you need the array of X, array of Y, and the description of the line, how you want the line to look like. If you are at this point and you are not so sure about things, you can go with online documentation. And plot and then what? Two-dimensional plots. Okay, right? Do not work to me, ask me about the command in MATLAB, in Octave, where you have a very good documentation. In MATLAB also documents everything very well. So Google first, alright? If you don't do that, you come to me, I will show you how to Google. These days is the day that you can find things very easily on. So here, let's take a look. This is the way that the X, which is the array, is defined. The X start from minus 10, the increment. So minus 10 and then minus 9.9, minus 9.8, and on until 0 and 10 all the way to 10. So you have this many X values. And then plot. In the plot, the first one define the value in the x-axis, so you can see that the extent is from minus 10 to 10, and the y values, which is the function values, is a sign of the x. So the sign is computed from the corresponding x value, and then x label is to label it x and label it y, and you put the title there. Actually, at the end of this plot, if you have comma and you can define how the line would look like, you can specify the line color. For example, you can scroll down and you can see the documentation is really good. Okay, use it. So go ahead and, well, many things you don't need to memorize things. Whenever you want to do things, you just need to search on the online documentation or on this documentation. It contains everything. So the line style there, if you want solid line there, the dash line, the dot line, the dash dot line, okay, you have all freedom. You don't really need Excel to do this, and well, the quality of the plot is really neat. So you need the X and Y, but for here I will make the temp X, temp Y, okay. Temp X is equal to zeros to 1. Well, it is a design. You are designing the building. You are an architect. You can select the room is here, the washroom is there. This is the same. You can do things in a different approach than mine. Fine, as long as you get the cat that will catch the mouse, the rats. All right. The Chinese word, they say that no matter what color and what pattern the cat is, as long as it catch the rats, that satisfies the requirement for a cat, right? So as long as you can get that plot, that's fine. But I just do this. I just set up the temporary array X and temporary array Y. So temp X, you will have two values. The first value will be from the starting node, X coordinate of the starting node, and the second value, which is this line here, is the X coordinate of the ending node. All right. So to get the X and Y coordinate, what do you call? You can obtain X and Y from here, but you will not obtain by hand. You obtain by algorithm. So X, Y core. All right. But which one? First of all, you know that now we are talking about X. You look at the XY core. The X is this column. So to get that column, it has to be comma 1, comma 1. All right. The easy part is gone. The first index, okay, the column index is gone, comma 1. How about the row? How do you select the right row? The right row comes from the element, the node number, right? Because one element connects two nodes. The first node comes from where? The node number comes from nmap. So this operation here for I equals to 1 to NELE, the operation is carried out from element to the next element. That means the I value tells us the current element that you are looking at. Okay, so nmap will give you the node number. Nmap, yeah, it will give you a node number. But what node? The node for which element? You know that it is for element number I. Okay, this is the element number I that we are looking at. When it starts I equals to 1, I equals to 1, you go to this nmap, to this line. You are working on element number 1. But here you are talking about the starting node, so that has to be comma 1. So nmap I comma 1, if I equals to 1, then it comes to that 6. Okay, I comment here that it is the X coordinate of starting node. Yeah, okay, I just do not want to exceed the column number 60, some magic number of mine. Actually, you can go through Okay, but I just want to make my code narrow like this. For some reason, I just don't want to exceed the number 60. Very stupid, superstitious guy. Is it superstitious? No, I don't believe that it's gonna affect my life, but I just love to see things in EG. Okay, ending node. Well, I make it coord like this, coord like this, easy to understand. TING, starting node. $60 or not? Oh, just right at 60. Okay. So we come over here. You got X, now you need Y, right? So temp Y and temp Y. Okay. Again. Oh, wait a minute. This one here, for the ending node, it has to be 2. Okay. Sorry. This has to come from end map number 2, column number 2. The comma 1 here refer to this first column in XY code. We are talking about the X. So it has to be comma 1 and the temp Y will be comma 2. So something like this could be the bug, and program will not report because it is the bug of the algorithm. You will find it when you plot out, and you will find what is this structure. It doesn't look even close to what you want. Okay, X and Y, 1 2 1 2 1 1 2 2, temp X temp Y. Now you can plot temp X comma temp Y comma. Inside here you will specify the format of your line. So I'm gonna need the solid line. I'm gonna need what color. You can add the marker if you want, but I don't want. So here is your choice. The color blue. Okay. Oops, wrong one. Blue. That's it. N. What? Not in function. N4. Okay. This seems to be a newer version of Octave. Oh, hey. We will see and expect that things can go wrong. That's life. That's programming. It takes so much time to save. Why is that? CLC main. Yeah. I add something. Axis equal control save. Yeah. So the scaling in X and in Y are identical. MATLAB can do much more. If you want to generate 100 figures, just come and code it up using Octave or MATLAB. You can make a contour plot. You can fill the color in here, and the color gradient will be provided by some command. Many things. If you want to put some sort of little circle there, well, to represent your node, it's possible. So go ahead, try it. It is very useful. And the figure here can be saved. You can make the GIF, PNG, TIFF if you want. EPS if you want the vector format. This will give you like a very sharp figures, because if you scale it up, scale it down, the vector format picture will remain that sharpness. But if you use the bitmap or JPEG, you scale it, you will lose the sharpness. And Octave file, the Octave figure file can be saved. This is a very good option, because once you save it in the, this is OFIG. In MATLAB it is called f.fig, .fig only. So you can come back later and then you can modify. You want to change the marker style, you want to do things, you can do that, and then you save to the picture format later. This format, the .fig or .ofig, you cannot copy and put it in Microsoft Word, Excel, because you will not see it like a figure. It is the data, the mathematical data in there, right? So you can save it. You can write the program to save it in multiple files if you want. So the structure, it looks good now. I guess we are doing the right input. So this point here, if you want, I call DMMY dummy equals to 1. Set DMMY to 0 if to turn off plot. So I put the if. I need to put the, if I'm not sure about if, then I go back here and then find if. The if statement, if, and then you got to put the condition inside the bracket, right? Documentation is this good. It explain much better than my explanation. Use it. And you can do many things like the if and else, okay? And then you can use the if and else, if and else. In case you have many conditions, you can use all of these, and you will have the how to say, switch statement. Let's see. No. While statement do until, okay. The operator, let's just compare. You don't find anything. You cannot compare the what is it called, to check true false, to, okay, it's not there. It needs some keyword, right? Logical statement. Okay, not this one. Logical values. Okay, logical statement is not there. Go, come back first. If the MMY is equal to 1, do I need the then? I don't think so. And if, okay, I just use the, is that the smart indent? Yeah, indent
Oh, it's different than MATLAB. Indent selection rigidly on indent. Okay. So it is easier for you to see to have the indent like this. So this line are encased inside this if, and these lines are encased inside this for. Basically, if you don't want to set the dummy here, you can set it here. So you type main 1 undefined near line 34 blah blah blah. What I did main and 1. Why is it? Oh, it clear all. Yeah. If it clear all, the things in the memory will be gone. After this line, you put the dummy there and then you clear all below, then it's gone. So try again. Yeah, it works. And next time, if you don't want, it doesn't plot. All right. So here you can just do it this way. Sometimes you can put the variable name, but generally for the main, you should like just change the number to change the option of the operation, option of the analysis. Just that. You do not want to put the x, y coordinate in that line. It is clumsy. We are done with the plot. And that is the option. If you want to open or close it. What else? We need to identify the properties of the cross section. So I call it EPRP, structural element properties. In here, well, if you want to put the data structure, that is cool. So if you want, you can do things like this: starting, ending. So you know that the first column is starting, second column is ending. This one as well. If you want, you put this like x and y coordinate, so you know the organization of the data. So structural element properties, of course, first what you need, the EA will be given manually. The L will be calculated. What else? You want the EA, you want the alpha, the coefficient of thermal expansion. Maybe we can play fun things from here, right? Thermal expansion is there. What else? Temperature will be like the load. It will not be the property, so I will not put the temperature change in here. Okay, I consider it a load. Creep, shrinkage, strain. What? Maybe just these two you can add later. So the EPRP start from the EA. This is the scale of EA. Well, take a look at the element number 1. Just one EA, 1.0, and alpha coefficient of thermal expansion. It is in the order of magnitude like 10 to the minus 5, 10 to the minus 6.
how do we input these kind of things? First, you can do like 0.1, 2, 3, 4, 5, like this. Confusing, difficult to recognize. Can it be better like 1e minus 5? Yeah, the program recognize this value, so you can use the scientific format 1.25 e minus 5. Alright, you can test your idea, you can check if things work in the way you want in this playground before you code it. So coefficient of thermal expansion is generally like 1 e minus 5, 10 micro strain per degree Celsius. Second element, what is the second? 3.0. And same material, 1 e minus 5. I'm gonna do this. This is gonna copy it down to here because everything is pretty much the same. Number 3 what? Number 3 3. Number 4 1. Number 5 1. Number 6 3. Number 7 1. Number 8 3. Number 9 1. Number 10 1. Number 11 3. Okay, so just boop, boop. Okay, 1 2 3. Oh, 1 2. 3 4 5 6. This is too smart. I don't want this. I need to hit enter every time. That wastes my time. Now, done with structural element properties. We will talk about load later. For now, as we have these things, we'll be able to establish the properties, the geometry. Geometrical properties of members. So this will be the calculation because we don't want to do things by hand anymore. Let's start. We need some array to store the length and the orientation. So GEOM, okay, sounds to be a good name. Geom is zeros. Zeros is to allocate the space for the array. What is the dimension of this array? If we have just the length and the alpha, just two things, so it will be 2 columns and how many rows? NELE, right? You need to be flexible, so NELE rows, comma 2. And then I need the del x. Well, I should make it DELY. No, it will be needed inside. So I think the structure will be like this. I'll just get the for loop over here. The operation is not far different from the indent code. Okay, the one before. So we are going to go through from I equals to 1 to NELE in order to calculate all the length. All right, and we're gonna need we don't need temp x, we need the delta x. I'll delete this because I don't need two values. I need how much is delta x. I'm gonna get the delta x square plus delta y square, take the square root, and then they get the length. So the delta x is equal to xy core, right? This one is for the first node minus this one for the second node. Close the bracket. Del y is equal to xy core first node, this is the y, minus we get delta x, we get delta y. We need the length. The length is inside geom. So geom data structure will be row indicates the row number corresponds to element number. First column I make it length, second column I make it alpha. So that is going to be comma 1 because we have the length. How about number of element? It comes from I in this loop. You can repeat, you can reuse it because the I is finished over there. You have N4, so the I value will be free. If you have the loop, for loop, and then you have the nested for. Nested for loop means you have for inside the for. Okay, we call it nested loop. If you have the for I and then the nested one, it is also for I. That's gonna lead you to the error message because you are going to manipulate the I value at the different place. All right. So you have for I, the next one has to be for j. Otherwise, your I value will be changed, and then once it go out there, then the I will not be increased by 1. It will be manipulated inside. Or you have a for I, and then you say that I equals to 5 inside the for loop. Something like that will cause you a problem. So you can just use the value of I, but you cannot specify the value of I inside. Geom I comma 1 is equal to, well, let's see, I'm not sure, sqrt, is it usable? Yes. Square root. Or if you want, you can take the whole thing and make it to the power of 0.5. But square root should be faster. And let's check in the documentation. Square. Least square. Mathematical operation. Oh, sparse matrix, huh? Sparse matrices. Mathematical equation, constant consideration. SQUARE. Let me try this.
Oh wow, what is square function belong to signal package? Okay. Okay. Fine. Just use this. The square of del x. Okay, then I do the del x times del x plus del y times del y. Actually, this is cheaper than the real square. You take the del x multiplied by del x is cheaper than del x and the hat 2, because the code, the computer treat it differently. For the exponential operation, you go through the different piece of code, but this is just the multiplication. Then we get geom. The next part is the geom I, 2. Geom I, 2 is tricky. Geom I, 2 will be taken from the angle, right? So how do you define the quadrant? Let me ask. The quadrant. The quadrant 1, x and y are greater than 0. Alright, 2, 3, 4. So we will find the angle and we will also check the quadrant, and then we'll be able to identify the right angle values. So before we go to geom I2, you're gonna have a lot of if you will have the logical operation as well, because you have the x condition and y condition. Alright, so if del x is greater than or equal to, let me check if it works this way. 1 is greater than or equal to 0. 1 means, I guess, yes. Yeah. 0. Okay. My brain has nothing. I never memorize things. If I want to know, I check and then I use, and then I forget it out very quickly to free up my space in the brain for imagination. And then I want to know something, I check it again. Not that good, but it works from my life. I want to know things, derive it again. so this class, it works this way. Derive every single thing. Oh, I forgot that. Derive. So that works. Del x is greater than 0. And how to use the and? Okay. Yeah, that is a stupid search keyword. Logical values and what? That should be some bit manipulation, numeric data type, content index, C false, double, single character. Yeah, if you want to know about the double precision, you can go check it like this. CE72.11 binary 64 value. Okay, read more if you want, but I don't want now. I want, or I think try. I remember it. Wait. Index. Maybe I search from the index. That could be one. Report about Octave package, contribute, donate. Yeah, sometimes if you feel good about it, you donate. You never do that. Well, once you earn. Yeah. or. Yeah, operator. Huh. Wow, what is this? This is the and. Which one is or? This one element result true and if both corresponding element of Boolean 1 and 2. Okay, element to if either of the corresponding okay, this is or. Okay, where is this thing? This thing is here. Alright, test it first. 1 is greater than 0 or 0 is greater than 1, and then I get 1. Okay, let me try it again. Minus 1 is greater than 0 or 0 greater than 1. You get false. Okay, yeah, it works. So this is the or. So if del x and del y is greater than 0, yeah, then what does this mean? X is greater than 0 and y is greater than 0, so you are in the first quadrant. Geom I comma 2 is equal to arctangent, check, I don't remember it, arctangent of 0, you're gonna get pi, arctangent infinity, you get pi over 2. So arctangent del y divided by del x. Let's put the absolute value, because if we consider the quadrant like this, then I just put the absolute value in there. Is that it? I guess so. Else if so I copy this. Oh no, I don't want on here, I want and, or it's not good for here. Okay, else if del x is equals to 0 and x is 0 and del y is greater than 0. I just want to make sure that everything goes right, so geom will be equal to what? If del x is 0 and y is more than 0, then it's gonna be pi over 2. Okay, if you want the pi number, you just go pi, and if it is too short, then you can say format long, and then let's see the pi. Okay, it gives you the longer format. If you don't want that, you can go back and format short again, then your pi value will be shorter. It just takes you more memory, right, to do that. Pi over 2. Else if del x is smaller than 0 and del y is still greater than 0. X is less than 0, it is on the second quadrant, and y is above 0.
the geom will be now it is different because right now you have the pi minus arctan of this value. Else if right now del x is less than 0 and del y is equal to 0, then geom is pi. Else if actually some cases it for example this one it might take care of this properly, but okay, I just split it off just in case. Don't want to think too much. Del x is of course right now less than 0. We are talking about the quadrant number 3, and del y is also less than 0. Geom will be what? Pi, and then add up, right, with arctangent. So you and then shoop, that angle. Those who watch the video will get what? So you shoop and boom, and that angle. Don't see the action, so don't get that. Well, fine, we'll find a way to. Else if y is less than 0 and x is equal to 0, y is less than 0, then (1.5) pi. Else, the last case, I don't think I need the else if, or well, just to make sure, else if del x is greater than 0. And del y is less than 0. Then geom I2 is equal to 2 times pi minus that arctangent and if and n for then okay, check for correctness. We need to plot geom. That's it. I don't put the semicolon on the back. Expect the bug, it might come here. Main, where's main 0. Hey, a bunch of bugs. And don't get scared. You never do things right at the first time, but you just need to learn your error and make it right next. So warning MATLAB style short circuit operation. What? Short circuit operation performed for operator call from line 69 column 4. Easy to track. 69 column 4. Where is it? Is it column 4? Else if, okay, go back and check that help on this. Else if come on, why is it
just if okay, if else. Oh, seriously, if else, seriously. Short circuit Boolean operation. Okay, combined with the implicit version of scalar value blah 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 blah. Octave short circuit Boolean operation work in this way. 1 and 2. The expression Boolean 1 is evaluated and converted to scalar using equivalent blah blah blah. If it is false, the value of our expression is 0. If it's 0, so what? It is evaluated and converted to scalar value. If it is true, the result of the overall expression is 1. Otherwise, the result overall is 0. Warning: this is one exception to the rule of evaluating all Boolean 1, which is the Boolean 1 is the empty matrix. The true value is always false. Empty matrix. Okay. Both operands may not be evaluated before determining the overall value. So inside it has to go like this. Okay, let me try. What it said is 69, right? It said the 69. Give it a try. Del let me try this first, if this helps. Okay, 69 still there, 69 still there. All right. Then I'll put the bracket like this. $69, $67. Yeah, 61 should be also there, right? 67, 69, 69. Let me check. Okay, just if only, just if. I don't why. And why is it just if? Okay, if and the condition and if matrix, if all matrix, okay, then body, all right, fine. Rem equals to, okay, so the equals has to be the double equal sign, which is correct already. I need the logical and we use this, and this is all. I think okay, I'll make it something like this. If you don't want this, but why? You can copy, you can paste, and you keep the original, and right, and 1,2. Okay. Maybe I shouldn't leave this blank. Oh, maybe. Let me try this first. It may not like the space. I'll see. So the line number 68, 70, 68. Okay. Check again. Does it have it has the space so it's okay. But inside maybe 68, 70, still 68 is a problem. Check. If 10, 18 already, the next class is coming up. Let me find. Okay, I will take logical.
So double and sign.
Double what?
Double and sign. And sign.
Double and sign, but and one, there's one place that shows only just one and sign. We can try double and sign. Sure. 70. Well, try if double and works, but then the different page, why was it just single and sign? Oh, great. Yeah, it works. So what is that documentation? Just single and sign. Yeah. So what is this? One. Oh, fine. Great. Thank you. So double and now we check element number 1. Good. We just finished it before that. Element number 1. Number 1. How is the orientation? The starting node of the number 1 is it is 6, 5. 6, 5. You can refer to what I had on the iPad. 6, 5. Then the angle will be pi over 1 pi minus that 53 degree, right? So 1 pi, which is 180 degree minus approximately 53 degree, you get 127. 127 multiplied by pi. The angle here shown on the second column is a radian angle, so you need to do this. 180 2.2. Well 5, 6 or 6, 5? 6, 5. 6, 5, then it should be 5.3. What is that? Let me check this one here. 5.3. What is that? 5.35. The answer plus pi. Let me try. 5.3. Okay, so I have to 1 pi in addition with this. Let me check. Geom plus 1 pi. Is there anything plus 1 pi? Plus 1 pi. It turns out to be this one. Del x is less than 0 and del y is less than 0. Okay, all right, got it. The way we set up the del x, we take the first node coordinate and minus the second node coordinate. We need to switch it around. Just that. So will be 2 and 2, 1 and 1. That's it. Okay, yeah. It is switched. Second node
if the first node comes first, then the vector is pointing to the first node rather than pointing towards the second node. Let's see the second element number 2. Number 2, 42 or 24. Number 2, 24. 24, that makes the angle equals to pi, right? And what did we get? Yeah, pi, 3.14. Number, what? Number 3, 6, 7. Angle is equal to 0. Yes, exactly. This is correct. The next one, number 4. 2, 3. Let's take a look at 2, 3. 2, 3 is pointing down in the quadrant number 4. So the value is equals to 2 pi minus that angle, right? 2 pi minus that angle 53 degrees. Well, multiply by what? Pi over 180. Okay, yeah, this one correct. Number 547. 47 is supposed to be the same thing. Yeah, okay, same orientation. Number 6, 54. 54, it has to be 0, right? Yeah. Number 7 is 15. It was supposed to be 53 degree. 53 degree multiplied by pi over 180. Okay, yes, correct. All right, so I think it's all in quite a very good shape. We will stop here, right? I'll upload this video